Agricultural Technology, Department of Animal Production, Alexandrian Higher Technological Institute, Thessaloniki, and he will give us a presentation on the study of the mode of inheritance of wheat field in Chios.
Ευχαριστώ πάρα πολύ, Γεωργία. Θέλω να ευχαριστήσω πρώτα απ' όλα τη στολίστριά μας για την εξαιρετική δουλειά που έχει κάνει. Ήταν φοβερή στο να μας συντονίσει όλος και να τρέξει το πρόγραμμα. Επίσης, να πω ότι νιώθω πολύ περήφανος που είμαι στο Ινστιτούτο σας, γιατί εδώ πέρα δούλεψαν μερικοί από τους, εγώ τους θεωρώ μέντορες μου, για παράδειγμα, ήταν από τα πρώτα ερευνητικά άρθρα που διάβασα ποτέ σαν ορκιακός φοιτητής, ο κ. Ανδρέας Μοχαγιάννης και ο στον χώρο. Είμαι πολύ περήφανος που έχω μια δημοσίευση μαζί τους. Ξεκινώντας από το πρόγραμμα της Φυλής Χίου, αυτοί μου δώσανε στην ουσία το ένασμα για να μελετήσω μια, πιστεύω, από τις πιο καταπληκτικές φυλές που υπάρχουν στον κόσμο. Θα δούμε τώρα πώς ο τρόπος κληρονόμησης στην ουσία της γαλακτοπαραγωγής, που είναι και το κυριότερο χαρακτηριστικό της φυλής Χίου. No, I'll do the rest of the presentation in English. According, as we heard before from the two previous speakers, according to the infinitesimal model theory, in the classical genetic model for the continuously distributed traits, the phenotypic value is the sum of the independent genetic component and environmental components. The genetic components are assumed to arise from a large, almost infinite number of loci, each one with small effect. Each effect is added to the other one. This model is actually the basis of the application of statistics into validated genetics by the early biometrician like Weinberg and Fisher and Wright, and it was later used for the development of predictive theory for the animal breeding, which has positive results in the genetic improvement of the livestock. Here we see some of the prediction models and how we started. We started with the contemporary comparison, then we moved to index selection, which for many years applied Dr. Mavrogenis in the Chios flock here, the mixed model equation of Henderson, the BLAP, and lately we use Bayesian methods for the estimation of breeding values. Then we had more computer power and we moved to multivariate methods. We can estimate breeding values for multiple traits simultaneously, so we have both heritability and genetic correlation. And because we had more information on multiple traits, we had higher genetic merit using multivariate methods. Here's an example of multivariate methods for chicken, for broiler chicken. So we have breeding values for body weight and for food conversion ratio, and we select the animals with the highest breeding values in both traits. So you can see the example of multivariate methods with two traits. We have 2 dimensions, 45 dimensions when we have up to 5 traits, 180 dimensions when we move to 8 traits. Things are getting more complicated and more computer intensive. However, they give us more information on breeding value, more accurate breeding values. And we move to 180 dimension mortality, for example, carcass yield, that's up back to 2001. We can go up to 15 traits with these ones using betting techniques and other techniques to have positive matrices, but however, that's the limit. The limitation, for example, is a limitation in the parameter space. You cannot estimate simultaneously more than 7 traits. Your problem is the positive matrix of the matrices. You can use betting techniques, but however, they introduce estimation biases. So there is limitation how much you can go multivariate and multivariate way. However, using all these techniques, we did pretty well, we see from the previous speakers. In the chicken, we almost increased our productivity by 300%. Cattle about 250, the genetic is about 200, about 200 in pigs. In salmon also, about 150. In fish, we're doing some efforts also in Greece using sea bass and sea breed fish species for farm species. And that's a very good example. For example, we see previously, that's a roast 308 chicken from Aviagen. That's a low Mandinka reverse layer chicken. They are the same age. The differences, all the differences, is due to genetic selection. The effect of genetic selection, quite substantial, I can say. However, using this infinitesimal model, this model cannot predict the likely limits of selection, except when we have very simplified conditions like Palmer effect. It is unable to predict the changes in reproductive fitness that might be expected that will accompany this selection. And this was said very early, but by a person that led from the institute, was later named Rosler, is the head of ILO, of Animal Breeding Research Organization, was probably Professor Christopher remembered. And it's only additive this model. What about dominance and epistasis? We don't take it into account, but we know where it is existing. So what we can do? Again, the example was set very early by Robertson again. In order to overcome this deficiency, it will be necessary to have description of the phenotypic variation in terms of individual loci affecting the trait. Nevertheless, the description of the genetic variation doesn't have to be complete, but we have to have at least demonstrate that a small number of genes have a major effect on the trait and consequently to the variance, to be able to map those genes and identify the mode of action given the existence of these genes. So the target was set quite early, however we didn't have the technology at that time. And examples of this, where this infinitesimal model fails to apply, is when a gene of large effect has a larger factor in individual trait. Genes of large effect of traits like color have been known to and used by the breeders for many years now in the traditional breeding. However, genes of large effect for commercial traits have been identified for some years now and can be easily incorporated to animal breeding programs. There are definitions of these major genes, as Desmond said before, but there are other ad hoc. They are changing and they are relative. For example, before there was even considering major gene only genes with huge effect. The latest, as the year were passing, definitions were becoming more, how you can say, to include big, smaller effects. So there are definitions like genes that have effect on the trait more than one phenotypic standard deviations, or like the Burula people said, that there is a difference, mean difference between the genotypes of the two homozygotes for the major gene, it's more than half of phenotypic standard deviation. However, all these definitions, I believe they're ad hoc and they will change over time as they change. What's the usefulness of these genes? To promote the genetic aid of animal breeding programs, and also is a tool to study the gene actions of the production and reproduction traits of the animals, and also to use the model organisms like mice, we can then transfer this knowledge to humans. Examples of major genes in animal productions: the dwarf gene in broilers that is used, also the double muscling gene that's later discovered as myostatin, the halothine gene in pigs, which you use FLP for the selection purposes, and also some in sheep, some litter-sized genes in merino breed, in Rowney, the Riverdale, the Thoka in the Icelandic, the Java in Fintail, the Orkuska breed, and also in the Cambridge breed, which I think this one is supposed to be the Burula integration of Burula. And then we have also in 2000 example of segregations of major genes in the famous Chios. That's, I believe, this is also the case for the Chios. However, we tested Burula, and it's not Burula, so it should be another mutation on the genome of this breed. But what about milk yield? In dairy cattle, as Desmond said, there are indications of major gene segregation for milk, and also QTLs on chromosomes, and many more on other breeds, and dairy cattle, you can find them in this database. In dairy sheep, in Ura breed, as Desmond said, that it was a study that came out during our project. They identified QTL on chromosome 6 by the Ascon publication, and also some earlier ones in a cross between Santa and Lacorn on chromosome 3, 16, and 20. All this for milk bead. However, a later study was not indicating a major gene segregation on uraprin where they identified QTLs. Now, maybe this one will make us worry, but I wouldn't think it would make us worry. So, we study an outbreak population of QC from the Institute of Agricultural Research of Cyprus, with pedigree reproduction record of 38 years from 1971 to 2009, with 10,000, approximately 10,000 records, approximately 7,000 repeated measurements of milk yield, fat content, liter weight, and birth. And we use animal model to estimate the polygenic heritability using a fixed effect years, seasonal lactation, and as a covariate, the days in milk, meaning the days that the sheep will milk. We use the program of Granevert, the field variance component estimation, PCA 4.25, for the estimation of the polygenic effect. We also done performed the segregation analysis, the same analysis that they use for the borula, identify the segregation of borula initially. And according to such analysis, a set of likelihoods for models of different modes of inheritance were maximized and compared for the best fit of the data. It's a Monte Carlo method, actually, I would say. And the one with the largest likelihood is the best fitting one. The best fitting model then is tested against a general non-genetic model to identify any departures from the particular hypothesis, for example, major gene. And thus we accept, when there is no departure from the hypothesis, we accept the null hypothesis by default. We use a Gibbs sampler for the Bayesian analysis. We estimate marginal posterior densities for the added effect, the dominance effect, the frequency of the genes, the variance controlled by the major gene, the variance provided for the polygenic component for the infinite number of loci, and the environmental variances. We use flat prior distributions, and after evaluations of Gibbs chains, 3 chains of 400,000 each, we burn in the initial 2,000 samples, and within 40 samples each Mendelian sample. By comparing Mendelian sample, for comparing the results, relaxation technique we used, and so non-Mendelian transmission of alleles were allowed. However, we sampled only from Mendelian samples were used in order to construct the marginal posterior densities. Fixed random effects were the same as the animal model. The program used was MAGIC by Jan et al. And we use also Gibb-Anal and match for a Gibbs chain evaluation, and last program for the construction of marginal posterior densities. Here we can see the distribution of the milk yield, and we can see some skewness distribution towards large milk yields, and that's one of the what makes you curious actually if there's a major what initiates the curiosity if there's a major gene segregating. For example, artisans are carriers of major gene. These animals are high yielders. Here we see the parameter estimates such as the polygenic model at the infinite number of loci. We had a heritability of 0.22 for the fat content, 0.06 for liter weight at birth, and 0.21 for milk yield, which is approximately what we expect. Here we see the posterior density for milk yield in our Cyprus population. We have a much more significant major gene component, much more than the polygenic. Okay, the model is not full, all the production of all the milk yield is not controlled by a major gene, but the major gene component is further far from zero, and it shows that it's much more important in controlling, much more significant controlling the milk yield. So we went up with the conclusion that there's a mixed model controlling the milk yield. There is a polygenic component from a small number of genes, and there also is a major gene affecting this trait. Similar results we had also after we done a Cox transformation to see, because these methods are usually affected by the normality of distribution. So because we had skew distribution, we've done a box scope transformation, we removed the skewness, we did the analysis, sorry, and we had exactly the same results, nothing changed. So there wasn't an effect from the normality of the distribution or to identifying it as a major G. And also if we see the fat content, we have a trailing head on this major G distribution. That's mostly the effect because we had to use fat percentages, so the normality wasn't as good. So I would be a bit cautious in making any inferences using from this analysis. So we need to further search in and identify if there are actually genes on the fat, for the fat content. But there is strong indications that this major gene is affecting the fat content also, and there are also references nowadays about genes with large effect on the fat content. Things more or the same. As you can see, this distribution for liter weight at birth more or the same. So if it includes zeros, that means that there's no significance of this distribution. So most component of liter weight at birth is polygenic, is controlled by a large number of genes. When we estimate the parameters for this analysis, by the Bayesian analysis, the mixed model analysis, the polygenic, the major gene component, when we use a polygenic major gene in our analysis, we had the polygenic heritability of 0.15, but when we include in the heritability estimate both polygenic and major gene component, we have a heritability of 0.47, which is estimates that Andreas Mavrogenis and Professor Paxtofor were getting in earlier studies. The additive effect of major gene was estimated to be 44.85 kilograms. However, there was a negative dominance effect. That was a surprising thing, and that mostly was hiding actually the major gene up to now, the negative dominance effect. The frequency of the major gene was estimated to be 0.73, so most probably the years of selection increased the frequency, but they never actually fixed it, maybe because of the negative dominance effect. Proportion of the active genetic variance explained by the major gene is 11%, quite strong effect. As Desmond said, it's more than half phenotypic standard deviation. Then what we did is we tried to see what's happening to other flocks, ARI-related flocks, and we analyzed data from an outbreak population of QC from the Chalkidiki Agricultural Research Station in Chalkidiki in Greece, and there's a pedigree and milk production records for 22 years. Here we didn't use the recent records because they dispersed the flock. Now the station is closed, and there were approximately 4,500 pedigree records, and milk production around 6,000 repeat measurements on milk yield. The model we used was the same fixed effects and covariates, and also in that population we can identify segregation of major gene much more significant than a polygenic component. Of course, the existence of polygenic component was still significant, but it was more significant the effect of the major gene. And we will plot the two posterior distributions together, the 4-protein posterior distribution for the two populations together, they're almost on top of each other, which that's not a coincidence, I believe. If we see the estimates from this analysis, here we have the separate population, polygenic heritability, total heritability, the additive effect, the frequency, and then negative dominant negative effect. Here the heritability in the Greek population, 0.17 the polygenic, 0.44 the heritability of polygenic and major gene. So there's very small differences. Additive effect is estimated higher in the Greek population. However, maybe that's the effect of the higher frequency that we can see in the Greek population, and again, negative dominance effect. So yeah, I've done it one by one. So, okay. What's next now? After we detect, we can see that there is a major gene segregation. Then we can do other candidate gene studies, as we saw. You'll see the later presentations and previous lessons I talk about them. You can do QTL detection using the daughter design. For example, what you do is you select RAMs that are segregating from for the major gene. How you select them? Well, you only look for heterozygotes in the markers, because those for homozygotes for the markers, they won't provide you any information. There will be no segregation. So these markers will be no use. And then how you will avoid these ones that are not homozygotes for the marker, they are heterozygotes. But however, they're homozygotes for the putative genes, and they don't provide you with any information in comparison with the total production. So you have to have only homozygotes, heterozygotes for the marker alleles, and also to be segregating for the putative major gene. How do you identify these ones? That's the question. Which linkage groups will search? That's another question. And also, how you can do it? Which we can do comparative mapping. We can use information from other species or information from the same species that are already detected, like Desmond I told you before. Which RAMs? Which RAMs to decide which ones are the heterozygotes? One solution that Bayesian analysis is providing us, providing with heterozyte probabilities from marginal posterior densities with the Bayesian analysis. And this is what we've done. Which from the posterior densities, we estimate the RAMs with the highest probability of being heterozygote. So these ones are the RAMs which we actually want to genotype in order to obtain the association with the major gene. So, in conclusion, there is a high probability of major gene segregation from milkweed in USC. It's verified in 2 populations. It seems to have a large effect. Probable carriers are available for further molecular genetic analysis for QTL detection in candidate gene studies that you will see later on. Thank you very much for your attention.
Thank you, Professor Chatziplis, for a very informative talk. Are there any questions from the audience? I think everyone wants to have a coffee now. So we'll take a break for about 20 minutes then. There's coffee and things to